I'll be talking about refinement in general and refinement in Phoenix. We have 1.5 hours to cover the topic, which is really not enough, but I hope we'll get somewhere. I realize the audience is quite broad and experienced. There are experts, there are novice people. So, and it's quite hard to to fit into that situation. So I'll try to do my best, cover basics and also some advanced topics, and we'll have some time to run tutorials and demonstrations. So feel free to ask your questions. Again, because it's nearly impossible to cover this large topic in about 1 hour, I'm really counting on your questions, specific problems and questions that you might have. Post them to the chat. I may not be able to follow the chat, but there is a great team around us, so they will look after questions, pick them up, and either stop me, which is great, or they can answer it after the formal presentation. Okay, so let's begin. So we're talking about refinement, and that's going to be crystallography case. Last time we talked about cryo, that's similar, but not exactly. So what is refinement, right? So refinement is, in case of crystallography, is basically a situation when you have your atomic model placed and built, and you want to fit it as good as possible to the experimental data. So basically that exaggerated picture illustrates the situation. So you have a model very close to the density map. You want to massage it into the map as good as possible. That's, in essence, that's what refinement is. Yeah. Now, just to put things in a greater and a bigger picture, that's an overall crystallography workflow, right? So basically going from crystallization data, solving phase problems, something that Randy and team and Tom talked about yesterday. A building model, improve maps build model, and toward the end, once you have your model very close to fit the data, that's where refinement comes into play. And I should say model validation. I'm not going to talk about it. Christopher Willems will talk later. So it's usually presented as a separate step, but it's not. So really, model refinement and validation are two steps that come together, and we usually do both interchangeably, right? Okay, so really, in a nutshell, that's the whole story about refinement. Very schematically, there are lots of great details going behind this picture, but very schematically, that's what it is. So you basically start out with your approximate model, which is not perfect, but kind of fits the data. You got experimental data, which structure factor, amplitudes, and intensities. You always, in refinement and program crystallography, at least, need to bring some additional information. We'll talk about it in greater details next. And then the whole idea is you're trying to change your model, specifically model parameters, to optimize some score. And that score basically tries to bring your model as close as possible to the data. So you do it iteratively many times, and you hope in the end to get an improved model that better fits the data. That's the whole story about refinement, really in a nutshell. Now, as I mentioned, refinement in crystallography and in cryo case are very similar, not identical. And we're not talking about cryo today, talking about crystallography. Just for the sake of completeness, I'm going to mention that conceptually, in both cases, refinements are very, very similar conceptually. The main difference comes in details of what's the experimental data. So in crystallography, the experimental data are diffraction intensities, and cryo are the reconstructions, three-dimensional reconstruction. So that's the conceptual main difference that makes refinement procedures different between crystallography and cryo, but the scheme remains the same. And in Phoenix, we have two tools that specifically address crystallographic refinement and cryo refinement. So both are available in Phoenix graphical user interface, and we will practice Phoenix Refine later today. They are next to each other in refinement section of the GUI. So Phoenix Refine is for reciprocal space refinement for crystallography, and real space refinement is what's referred to refinement in real space against the map. So both are available and next to each other. As I said, that's a very big topic, very hard to talk about everything. So that's why I'm sending you pointers to reading. So those who wants to drill down more and learn about greater details about how things work and all the other details, you can learn about real space refinement. There's a paper we published a year ago. And there's a paper we published about 10 years ago about Phoenix Refine, that's crystallographic refinement. So these two papers are your starting points if you'd like to learn about refinement more than I mentioned today. Okay, so my plan for today is to go through these steps of refinement procedure and talk a little bit of each of them. And then in the remaining time, which I hope we'll have about half an hour, maybe 25 minutes or so, depends, where we'll run tutorials and actually practice doing refinement. So I'll go one by one very quickly. And yeah, we can ask questions meanwhile, and I count on the team to stop me and answer the questions. So let's talk about model. What is model? What exactly it is? Well, we talk about crystal, and protein crystals are liquid crystals essentially. They contain a lot of solvent, and from statistical surveys we know typical protein crystals contain about 50% of solvent occupied the entire volume. So that's a lot of solvent, and there's a macromolecule, of course, right? So when it comes to modeling crystal structure, really not think only about protein model, but we also need to think about something else, which is bulk solvent. So the model here that comes into refinement is actually two contributions that arises from atomic model and bulk solvent. And that's very important. And that's a common misconception. People always think your model is atomic model, your atoms, your protein, your DNA, RNA. But on the other half is actually what probably least interesting, right? So it's a bulk solvent, it's not a structural thing in a crystal, why you care, but because it occupies almost half of the volume of the unit cell, it is important to care about. Right. Now let's talk about model, atomic model. Again, this is very basics, just to get everybody up to speed. So yeah, that's how we represent atomic models. These are a bunch of dots connected to each other via covalent links. These are atoms, and each atom in the models that we use is described by its position, its coordinates in Cartesian framework, and that's a snap. That's the copy of atom representation of PDB file. So the coordinates and uncertainty in the coordinates. And this uncertainty is described in two ways, which I'll explain in the next few slides, which basically it represents local atomic vibrations. So, and larger scale vibrations. So the same atom across all unit cells may not occupy the exact same position. And to reflect that fact, there are two parameters that tries to account for this, and I'll explain that in the next few slides. Okay, here's the idea, and I know it's obvious, but not to everybody, so I mentioned that. So a crystal is a collection of many unit cells, right? And each unit cell has a copy or copies of your structure, your molecule, right? And all these copies are very similar, but not necessarily identical. When it comes to your crystallographic structure solution, you get just one structure, one molecule, which is an average across all unit cells. So if you think about it, it's basically if you just take each structure from each unit cell of the crystal and superpose them, you'll get something like this. So in most places, you'll have a very good match, and some atoms are going to be different across all unit cells. And that's basically what we call our disorder. Now, as I said 2 slides away, there are two ways to account for this fact, and that depends on the magnitude of the difference between atomic positions across all copies in the unit cell. So we refer to large scale disorder and small disorder. So for the large disorder, really what we think of that you can distinguish particular individual locations of atoms in the map. Like in this exaggerated example, where for the phenylalanine side chain, you have pretty much 2 distinct conformations, right? So this we model with alternative conformations, and parameter that describes the situation is called occupancy. So in this particular example, it's not really accurate because here we have two instances of the side chain. And in your PDB file, you have 2 atom records with 2 copies of the same atom ID, different coordinates. Then we have different B factor, and the occupancy factor would reflect the probability of each conformer to occupy its space. So for example, one can have 0.3 and the other one can have 1 minus 0.3, 0.7, right? So that's for the large scale disorder. For the small disorder, something like this, where you kind of see the side chain is blurred. There's no one distinct position for a particular atom of it. We use B factor to describe the situation. And B factor can be, depending on the data resolution, data quality you have, it can be approximated as just one sphere, or if the data resolution is high enough, it can be what we call an isotropic, and it can be an ellipsoid. So if you have a isotropic B factor, you'll have just one number in your PDB record, in atom record, right? That's the B factor. If you represent your B factors as anisotropic, you'll have 6 elements describing the anisotropic B factor, the ellipsoids. Yeah. Now, just a little bit more about B factors, because that will come to you eventually when you choose refinement strategies, when you do refinements. So if you think about it, let's consider the side chain here. So this atom here, right? It can vibrate on its own. It can move on its own, right? But it also belongs to a whole side chain, and the whole side chain can undergo some oscillations or librations around torsion angles. So you already have 2 contributions to motion of this atom, its own vibration plus vibration as part of the whole side chain. Now, the whole side chain belongs to domain or a chain, protein, and chain belongs to the whole molecule. So there's a nested contribution of motions that go into atomic B factors. And when it comes to modeling, when it comes to parameterization, that means the atomic B factor is basically superposition of several motions, again arising from its own vibration plus some other contributions. So in reality, we are not as detailed as I described. So we basically can model in refinement local atomic vibrations, which can be isotropic or anisotropic. And we can assume that the atom belongs to a bigger group that vibrates, that moves on its own as a rigid body. And that is called TLS. And that's what goes to the total B factor. So that's a bit of complicated topic, could be a lecture on its own, but just to give you a concept that don't think of B factor as just one thing. It has several contributions to it. And these contributions have different physical nature. And what we can do in refinement, we can model essentially 2 of these contributions, the local atomic displacements and anything that comes from a global concerted motion. Okay, let's move on and let's talk a little bit about experimental data. Good. Well, let's think a little deeper into this topic and think where the data comes from and why. So we deal with crystals, and crystals composed of unit cells. These are periodic objects, right? And this fact has 2 consequences. Well, first, we can do diffraction experiment because crystals are periodic objects. And the other one is that the electron density distribution in the crystal can be represented as 3-dimensional infinite Fourier series. This is just a formula taken from a regular textbook on crystallography. So what we have here, we have a sum over infinite number of Miller indices. And there are 2 components here which are very important. The structure factor amplitude, this is something we measure in experiment, and the phase. Now, very important part to realize that in experiment, we only measure, from the experiment, we only get structure factor intensities, amplitudes, and not infinite amount of those, but only finite amount. And we lose the phase, and that's what's called phase problem in crystallography. We lose this term during the experiment. And so what that means is, if we only get structure factor amplitudes, but don't have a phase, we cannot calculate electron distribution in the crystal. So that's exactly why we need to employ all these methods that Tom and Phaser team talked about yesterday to solve phase problem using experimental phasing or molecular replacement to get these phases. Right, but your experimental data are these terms that come from experiment. So that's what it is. Now let's talk about score. What it is. Well, basically, as I just said, from experimental setup, you get your data, which we refer to as FOBs, which is an array of structure factor intensities or amplitudes. And turns out if you have an approximate model, which is your macromolecule sitting in the crystal with bulk solvent around it, you can calculate, and we talk about how you calculate it a bit later, you can calculate structure factor from your model. Now, once you have this two, it's kind of obvious, I hope, that if you want to model matched experimental data as best as you can, you want this F model to match FOPS as best you can. That's the objective of refinement. So you can put together a function, a mathematical expression that will formulate this objective. So you can define a least squares target function to fit your F model to FOPS. You can define R factor, but in reality, actually use maximum likelihood target functions, which are versions of this, but are smart about errors and other nuances. But conceptually, that's the idea. So you got your experimental data, you got your model. From the model, you can calculate structure factors, and you can attempt to match them against the experimental data. That's the concept. That's the concept of the score. And again, scores can be as simple as R factor or least squares target function, but in reality, in refinements, we use more complex versions of this called maximum likelihood target functions. Now, so I mentioned you can calculate structure factor from your crystal structure model. Now, the question would be, how do we do this actually? And I need to explain it in the next slides. As I said, the crystal content is a contribution of two parts, right? So it's a macromolecule, that's your macromolecule, and a bulk solvent. So the total model structure factor that accounts the entire contribution of the crystal is some scale plus structure factor that arises from atoms here, and structure factors that arise from bulk solvent. That's the idea. That's a very high level picture. Now, how we actually do this? Just a little bit lower level detail, which is totally trivial. It's very simple. So remember, I showed you atomic parameters, positions of atoms, and some parameters that describe disorder, like occupancy and B factors. So basically, if you look at any crystallographic standard textbook, you'll find the formula for the structure factor, F-calc, that relates all these parameters together. And basically, that's the sum of all atoms. This is where atom type goes in. That's the form factor. That's the scattering factor that describes how your atom scatters in the diffraction experiment. That's where occupancy goes in. That's the B factor term. And that's where the coordinate, that's the phase term. That's where the coordinates go into this formula. So looks pretty trivial, right? So you have atomic parameters, coordinates, B factors, occupancies, use this formula. And here you go, you calculate your F-calc for atomic part of your F model. Now, what do we do for for the bulk solvent, how we calculate the bulk solvent contribution. And that's how we do it. That's how most crystallographic packages, refinement packages do this. I'm meaning Phoenix, Refmark, Explorer CNS. I think Shellix does it differently, slightly, but that's the idea. So you basically assume that bulk solvent is flat, so there's no variation of electron density inside a bulk solvent region, and these are the steps that do the job. So basically, we define a three-dimensional function which we call solvent mask, which is a binary function, has zeros inside protein region and all ones, all units inside the bulk solvent region. That's our three-dimensional binary function. We take the Fourier transform of this function to get structure factors from it. Now we find an optimal scale to add the structure factors to the FCalc, to the atomic model structure factors, by fitting F model to F obs. And once we found the optimal scale, we have our bulk solvent contribution. So now we can calculate the whole crystal structure model for structure factors that accounts for everything in your crystal atoms and bulk solvent. All right, so that's the concept. That's how we do this. Great. Okay, that was data and that was score. Let's talk about additional information. So what is this? Why it's important? Why we need it? Right. So as I said before, the experimental data that we obtain has finite resolution, so we don't measure all the infinite amount of reflections. We always measure some reflections in the evil sphere, if you know the theory, what I mean. So you don't get all the reflections in the diffraction experiment. So that's what's called resolution. So the data we measure obviously has experimental errors, and the amount of data typically in case of macromolecular crystallography is less than amount of model parameters. So there is a risk of overfitting. So these are all three major deficiencies of the experimental data. Now the phases can come from molecular replacement, or they can come from the experiment and from your preliminary model, and therefore they always have errors, right? And if you remember that formula that I showed you a few slides away from now, you use experimental structure factor magnitudes of OPS and phases to calculate a map. So all these errors do contribute to how your map looks like, right? And here's just an illustration that reflects the resolution, but if you add experimental and all other errors, that can be even worse. So at 1 angstrom resolution, you know, your map looks like, this is just an example for phenylalanine side chain part of the ring. So, you know, 1 angstrom resolution is quite high. You can resolve individual atoms. You know, if you have errors, they may be resolved better or worse. As you go lower in resolution, you get a less detailed map. And as you go even to lower resolution, you get even less detailed map. Now, we're talking about refinement as a procedure that moves atoms or fits atomic parameters to fit the map. So in this case, if you get these atoms and you want to move them to fit the map as good as possible, it's pretty obvious, right? So there are picks here, you know exactly where the atoms are. It's all obvious, all good. In contrast, in this scenario, you kind of know where the sidechain is, right? So that's the blob, that's where the sidechain belongs to, but you don't really, if you ask where this particular atom needs to be, you won't be able to tell just based on the map. It can be here, it can be here, it can be there, it can be anywhere. The map doesn't tell you where it is. So to make refinement possible in this situation, you need to bring some more information, some extra information. And that's what restraints or constraints are about, and that's what this additional information is about. So you need to bring something else most of the time when you do crystallographic refinement, because the amount of information, the quality of information that comes from experimental data is never sufficient to unambiguously define your structure. And that's even worse as you go to low resolutions, right? So at some point you stop seeing particular groups of atoms, like 4/5 angstrom resolution is non-limit to stop seeing side chains. For example, you see sausages of density for the main chain, but you don't see side chains. And going to lower resolutions, you start seeing envelopes for the entire molecule, but you don't see the high-level details. And that's exactly why you need to have restraints. And that's my favorite example that I've been showing for 10 years now. It illustrates the importance of restraints. Why? What happens if you don't bring this extra information? So what happens why in refinement, right? And here in this little numeric toy example, we're going to feed this perfect alpha helix in a sausage of density of, I think it's 5 angstrom resolution. So without bringing the information into this refinement process, that this is actually the alpha helix. We just place some bunch of atoms that represent alpha helix to begin with, but we don't tell the refinement procedure that this is an alpha helix. And this is what's going to happen. So the refinement is going to optimize the structure against the map as good as possible, as good as it can. But because it doesn't know a priori that this is an alpha helix, it's going to do what it can, but the result is not going to look like an alpha helix. And this is not what you want to have as a result of your refinement, right? So that's exactly why we need to bring this extra information, which are chemical and generally geometrical restraints. And there's a whole bunch of different sources of this information that can come into refinement. Very basic one that we always use in macromolecular crystallography, there's restraints on covalent geometry, which basically says, enforces particular bond lengths and angles and facts that some groups may be planar and so on. But there are some extra restraints that are important if you refine against low resolution data, such as restraints on side chain distributions, Rotamer restraints. We know about Raman plots, and that's a very strong source of information that can be used for validation, but can also help refinement. We know about protein secondary structure. That's also a very strong source of information that can be used in refinement. Internal symmetry, which we refer to non-crystallographic symmetry, NCS. Your molecule may have similar copies, identical copies. And that information can also be explored in refinement. And also things like if you you define your structure, but there's a similar structure that somebody solved already before, you solved it before, you can, and that structure is of high resolution or better quality or something like that, then you can use that structure to help your low resolution refinement using information from that structure. So there's all information, there's all the extra information that goes into refinement and can help refinement. Now, just a technical detail, so everybody's on the same page. So this information goes to the total score function, to the total target function, as just an extra term, which is called restraints. Right, remember we had a score function that relates structure factors obtained in this experiment and calculated from the model, and we have some extra information that comes into it. So this extra information goes as extra term here with some particular weight, and it's just a sum of different contributions, accounting for covalent bond lengths, angles, planes, secondary structure, Machamon plot, and so on. Right. So that's how it's done technically. Now, at this point, to mention the difference about constraints and restraints. As I said, we want to explore all information that we can in refinement to make it stable, right? And if your structure has similar copies, that information can actually be used in refinement in two ways. So you can ask refinement to treat these copies as approximately similar, but not necessarily identical. And that's what we refer to as restraints. Or if resolution is, data resolution is relatively low, and by that I mean 3.54 and lower, then the detail, the differences between copies may not be distinguishable, and you may ask refinement to treat these copies as identical because you don't have experimental data to explain the difference between copies. And in that case, you would be using constraints. So that's the important difference between restraints and constraints, because I keep seeing people misusing these terms, and I felt like I mentioned what the difference is and why. Okay, well, I've been talking about restraints on B factor, on atomic model geometry and stereochemistry, but we also, B factors are also refinable parameters, are the parameters of your atomic model, right? So, and we also refine them, and we also want to make sure they are meaningful, right? So we also apply restraints on atomic displacement parameters, and this little picture illustrates the concept, right? So but essentially, B factors cannot be very different for atoms that are covalently bonded. Why? Is because if you have very different B factor for atoms that are covalently bonded, what that means this atom moves a lot, and this atom doesn't move pretty much at all, or move just a little. And what that means, in turn, that means that the fact that this atom moves a lot, it stretches its covalent bond. We know covalent bonds are very strong, pretty much not stretchable, which, that doesn't make chemical or physical sense to happen. So we try to avoid a situation having very different B factors across linked atoms. So we apply restraints on B factors to make them approximately similar. And this is for isotropic B factors, and same concept for anisotropic B factors. So anisotropic B factors are ellipsoids, right? And we want these ellipsoids to make physical sense for bounded atoms. For example, this kind of situation is nearly impossible that atoms move out of spatial thing. B factors on sphericity and so on. So for example, you can, if the data isn't great enough, your atomic B factor may refine to something that would look very physically implausible, like a long stick or plate or something else. Okay, moving on. So what is modify model parameter stage in this process of refinement? So what is this? Well, basically, the refinement target function that I just mentioned to you, is very complex and has multi-dimensional profile, has a lot of peaks, it has a lot of dips, and has a lot of, basically, it has a lot of local minima. If you take a slice through this multi-dimensional space, you'll look into something like this, where that's your refinement target function. It has lots of local minima, right? And the goal of refinement to get to the deepest possible minimum. Hopefully you get to the global minimum, which never happens, but that's the goal, right? And to make this happen, there are different tools, optimization methods, which are mathematical procedures to optimize your target to get you to the deepest possible minimum. That's the objective of that stage, to change model parameters to get to the deepest local minimum. So doing refinement, you'll definitely hear of different optimization methods, primarily gradient minimization or simulated annealing, grid searches, and doing things by hand using code. And this little picture tells you the major differences between these two methods. So when you run refinement, you usually just do minimization. And what that is basically you start out here, and by the nature of minimization, you can only get to the nearest local minimum. You cannot get here, you cannot get here, you cannot get here, right? So, but that's where you want to get. So, but that's how much gradient minimization can do for you. There are more advanced tools to overcome this problem called simulated annealing, which is a method that allows you to do optimization in a way that you can actually escape local minima and eventually get to deeper local minimum. That's what simulated annealing does for you. And in some cases, when you have a few parameters to optimize, you can actually do the grid search. You can, I'll explain that in a second. You can basically just sample the space and see if you can find the deepest one, the deepest minimum. You cannot sample the entire space, so you may not get to the global minimum, but you sample the space in some reasonable range in a hope that you get into the deeper minimum. So that's what the grid search is. And by the way, every time you move your structure in Qt, you do pretty much versions of this, but you do it by hand using your eyes and mind and Qt. Now, just to illustrate this point, what's the difference between these different methods? In reality, what that really means. Here we consider 3 situations of a side chain not fitting the map, right? So in this picture on the left, the side chain does not fit the map, but it needs just a little bit of movement to fit the map. So in this case, minimization can do the job or simulate annealing. So that's an easy job to fix for minimization. Now, if you have something like this in the middle, then it's very unlikely that minimization is going to move the sidechain into the density because it's too far away. So it requires moving the sidechain requires jumping over energy barriers, peaks and holes of the energy landscape to move the sidechain into the density. So simulated annealing is likely to snag the sidechain into the map, but pretty much sure minimization is not going to. And now if you have something like this on the left, on the right, the sidechain and the density are far enough from each other, then it's very unlikely that simulated annealing does the job, and definitely minimization is not going to. And this is where the grid search comes handy, because you can sample the long torsion angles and fit the sidechain into the map. So that's the illustration of different optimization methods that we routinely use in refinement. Sometimes we use them automatically, sometimes we rely on users to choose to use them, but these are your choices, and this is what really is behind the scene. Okay, so just to summarize, so we basically went through all the steps of refinement, and just recap again. So the model is not your just atomic model, but keep in mind, model is all in crystallography at least. Model is always your atomic model plus bulk solvent. That's totally critical to think about this way. So the bulk solvent is important. It's half of your scattering contribution. Experimental data, that's what comes from experiment. Never perfect, finite resolution, different pathologies, errors. Additional information, restraints. That's what you always need to bring into refinement and dose it appropriately. The score function is something that relates model to experimental data, and you modify your model parameters to optimize the score function. And that's the essence of refinement. And by doing this, you hope to get the improved model. That's what refinement is about in a grand scale. Now, let's go back to Earth and talk about and think about some practical considerations when it comes to actually doing refinement in your regular routines. And here I have just a few slides of a collection of some random considerations, not a full complete list. And you can bring more with your questions, obviously, but I'll go through this and hope you ask more questions about this aspects. So the refinement is highly automated, but clearly there's a lot of decision making that is expected from the user. So I would say refinement is the least automated step in the entire pipeline of structure solution. So things like molecular replacement and automated model building, density modification, these are very, very automated tools where you rarely need to change low-level default settings. I mean, you need to adjust some parameters, some very basic parameters, how many copies of particular thing you have, but this is pretty much it. While in refinement, you need to do a lot of decision making, such as how you parameterize your model, what's my resolution, depending on resolution, what strategy you choose. There's a lot of stuff you need to think about in refinement. Yeah. Run Xtriage. I think people mentioned that before, and I will reiterate it now. So before you run refinement, you really need to have an idea what to expect, what's your data quality is, and that's totally important, because that sets your expectation. For example, if you have tweening, then you need to choose appropriate strategy for refinement. And how you know you have tweening? Well, you need to run Xtriage. You're not going to know about tweening unless you try to learn about it. And anisotropy and completeness and all other things are very relevant to this. So same goes here about model parameterization. Really, you need to use something that is appropriate for the resolution and stage of refinement. For example, there's a very classical question about using isotropic versus anisotropic B factors, and that decision is made based on the data resolution, right? So, and also the stage, actually, stage of refinement you are at. So if you refine your structure at 1 angstrom resolution, but you are far away from having your final structure, you probably don't want to use anisotropic B factors. But towards the end, you definitely want to. Things like this, right? So use optimization method as appropriate for the refinement stage. Classic example here would be us using simulated annealing, right? So as I said, simulated annealing is very powerful method to get your model closer to the data, but it's very aggressive method. It shakes your model up a lot, and in the hope that it can, escape local minima and bring your model close to the data. But if you are near to completion, if your structure is almost final, you don't want to shake it up a lot, because there's no guarantee it comes back to the original stage, right? So you probably don't want to use simulated annealing towards the end of refinement, while it's very likely you want to use it in the beginning stages. So you need to think of optimization methods depending where you are with refinement. Oops. Now this is a popular topic that comes up in mailing lists every time. So use hydrogens. Yes, do use hydrogens, but do it wisely. Use them when your atomic model is near to final. So if you have very crude model with lots of clashes where you need to rebuild a lot of stuff, and you expect the model to change a lot, it's probably doesn't make sense to use hydrogens, because that does add complexity to your structure. But when your model is close to final, we know hydrogens are there, and it's always, regardless of the resolution, is a good idea to use hydrogens. So this is just a collection of facts, right? So half of the atoms, protein hydrogens, you count for the half of atoms in protein molecule, right? They do a lot of interactions, play biological role as well. So it's just a, an illustration left and right with and without hydrogen. And you see how empty the model without hydrogens and how crowded it is with hydrogens. So if you don't have hydrogens put onto your model, the atoms can come closer together because they don't know there are hydrogens. Refinement doesn't know there are hydrogens if you don't have them explicitly. And you get all the clashes, all the stereochemical unfavored clashes that you don't want to have. So you do need to have hydrogens towards the end if you want to have your model be meaningful. Very important. Now, know when you stop. That's a big topic, and basically that means you keep refining the structure and keep going on and on and on and on, and you wonder, am I done yet? Am I finished? When do I stop? It's a good question, and one way to answer this question is to, and there's a tool to do this in Phoenix, I'll show you in a minute, is basically look at all other structures in the protein database of similar resolution and see what parameters they have. So say if you refine your structure at 2 angstrom resolution and you get a particular R factor, it would make sense to go to the PDB and look at few thousands of other structures at 2 angstrom resolution and see what R factors they have. And that statistically might suggest you whether you are in a ballpark or not. So that's the idea. And we have a tool in Phoenix that I believe is underused, should be used more, because that really tells you something about where to stop and when to stop and whether you're ready to stop. It's called Polygon. Basically, that's the concept, that's the idea. So it's a graphical picture with this rays here, bar, so that we call them. And each bar represent a histogram of a particular metric. So this bar represents average B factor with the the Gaussian distribution in the middle. This one shows R work, this one shows R free, and bond angle RMSDs. And then you have dots on each bar that shows where your particular model is with respect to all other structures in the PDB at this particular resolution, right? So that how you interpret this. So if your dots are approximately in the middle, that means you're very, very similar to all other structures in the protein database. So which is good. That means, you don't have any pathologies, anything outstanding. If you have something that's shown on this picture, that means that's very suspicious. You have R work, which is way larger than all other structures in the protein database. That's suspicious. Same with R free and all other parameters. So just to reiterate what I just said, if you got a polygon which looks like this, that means you are very good. You are very similar to what all other final structures, by the way, in the PDB. So you may want to look into local details and map fittings and such, but that means you don't have anything outstanding in your structure at this point. However, if you have something like this on the right, that means there are issues. Your R work, your R3 are way too high compared to all other structures in the PDB. The average B factor is very high compared to all other structures in PDB. So that means your situation is very unusual. It doesn't mean it's wrong. Maybe there's an explanation why it is, but that means you're very unusual, and chances are you'll have to explain why there's this. Just keeping going about practical stuff. Well, restraints and constraints. That's the key, and that's what guides refinement. NCS, things you need to really think yourself, and this is kind of what software does not do for you, are decisions about whether to use non-crystallographic symmetry or not. Non-crystallographic symmetry we refer to NCS. So basically the rule of thumb here is if you have high enough resolution data, you don't need to use NCS. What is high enough? That's a good question. I would call it anything better than 2 angstrom, but that's very subjective. Some other people could say 1.8, some others would say 2.5. So my vision is, I would say it's 2 angstrom resolution. Higher than 2 angstrom resolution, you probably don't need to use NCS. Now, you can use NCS as constraints or restraints. So you definitely use NCS restraints for anything that is lower than 2 angstrom. But what if you have 4 angstrom resolution data or 4 or 5 angstrom resolution data? That kind of resolution data would not allow you to tell differences between copies that are NCS related. So at that resolution, you may want to use constraints instead of restraints. So that's kind of things you need to think about when you decide about using NCS. And this is something that you need to think about. Software is not going to do it for you. The secondary structure restraints is conceptually very similar. So basically, it's a point when map does not allow you to see the differences and details of secondary structure geometry. And once the map stops, telling you about secondary structure geometry, it can go wrong in refinement. And that means you need to help refinement by using secondary structure restraints. We're talking about resolutions of 3, 3.5, 4, and similar. Now, very same point about Ramachandran plot restraints. You don't want to bias your Ramachandran plot by using Ramachandran plot restraints at high resolution or medium resolution. But if you work with low resolution data, chances are you need to use Ramachandran plot restraints very high. So that's just a consideration that you need to keep in mind. Now, well, there's important nuance about Ramachandran plot restraints. The point and the thing is, it's very easy to abuse these restraints to achieve something that you may think is good, but it's not. That's the point. So, and the picture below tries to illustrate this point. So for example, if you have something like this, there's an original structure, that's a real structure taken from PDB. I don't remember whether it's Xtallography and Karian, doesn't matter. So this structure has an awful amount of Ramachandran outliers. And of course, you don't like it. And your desire is to get rid of these outliers, right? So, so one way to do this is abuse restraints and say, well, I just take the structure and turn on Rama channel plot restraints and let them do the job. So that's abusing Rama channel plot restraints. So what you'll get in the end, you'll get something that looks like this. That looks great for some, but definitely not to me. Why? Because sure, you got rid of all these outliers. That's great, but the plot doesn't look natural. The plot doesn't look like a good-looking Rama channel plot. Not because it has this few outliers, not at all, but because it has this residues clustering on the borders. You have residues avoiding some particular region of the plot. So this plot does not look like a good looking Rama channel plot. And what is good looking Rama channel plot is this. So we know how good looking plots appear. Now, of course, you can say, well, that's not obvious. That takes a trained eye to tell. Well, the bottom line message is don't use Rama channel plot restraints to fix problems. Do use restraints to keep good structure good. So for example, if you refine against low resolution data and it fixed everything, all the problems in the structure, if you run refinement without Rama channel plot restraints, you may get all these outliers back. And that's something you don't want to happen. So that's the valid situation to use Rama channel plot restraints. But if you have, something like this to begin with, you do not want to use Rama channel plot restraints to address the problem in inverted commas, right? So you really want to fix these outliers yourself first, then run refinement to make sure they are snug in place, but you don't want to force these outliers blindly to go into allowed regions. Now, just to mention to you, and this is very, very recent development in Phoenix, published this year, just a few months ago. So you may wonder, looking at this plot, you may say, well, how I know this plot is bad? Because, naively, you can look at this plot and say, well, everything is, allowed or favorite region. I have just a few outliers that I can fix, or maybe just leave them be around. So overall, this looks great. So, but it's not. It's very bad. So how you know it's bad? And we have the answer for you. So we developed a tool. Oleg Sobolov developed a tool that basically, and it's available in Phoenix, that allows you to supply structure, and that tool will tell you whether the Rama channel plot distribution corresponding to that structure is meaningful or not. So I totally recommend this paper to read for everybody on this chart, because that really will give you an idea of how to interpret and how to make sense of various flavors of Rama channel plots. So, very good paper. Check it out. Okay, towards the end of my formal talk presentation, before I run into doing tutorials, very important, as I said, there's no chance I could cover all the topics in any depth. So that means you can always ask questions. There are channels for you to ask questions on Phoenix mailing list. It's open to everybody. So whatever you ask on Phoenix mailing list will reach everybody, developers and users. You can be more discreet, asking, reporting bugs, ask questions on dedicated channels, help at Phoenix or bugs in Phoenix. Very important consideration when you report a problem or bug, ask for help. Just think about it. We can't help you if you don't help us to understand your problem. That's very fundamental to asking questions or reporting back. So if you just tell me that something failed and you are stuck, I'm sorry for that, but I cannot help you because you have not provided me with enough details to help you. So if you reach us out with your problem or question and you expect us to help you, these are the steps that you need to follow. And that will pretty much guarantee we can do something for you. So you tell us what Phoenix you use, Phoenix version you use, you tell us what parameters you use, what command line you use, you send us all input and output files, literally all input and output files. And you clearly explain the problem. And you explain it in a way that we can take your files and actually reproduce the problem. So literally that's what we need. If we cannot do this, chances are we cannot help you with your question or problem. So that's totally important to realize. Okay, that's the generic slide. Always show your part of Phoenix, great family of tools and developers with great financial support. All right, I'm done with my formal talking. I'm happy to someone to go ahead and go over the questions. I'm going to answer all the questions, and then I'll be running some few demonstrations of Phoenix Refine.
So there are, yeah, well, we're running a bit behind, but let's go through a few questions now, and then that'll just come out of our question time from later on. So there was a question early on about resolution recommendations for anisotropic or TLS refinement.
Right, so for doing individual anisotropic B-factor refinement, you're thinking about resolution range of 1.5, 1.7 angstrom. That's 1.7, 1.6 and higher. That's where you do individual anisotropic B-factor refinement. And to do TLS, it doesn't really matter. So if you can do it at any resolution conceptually.
Yeah, there's a related question. At which point is it better to run TLS parameter to run TLS?
Towards the end of refinement, that's for sure. Again, that's because conceptually, if you do TLS parameterization, you introduce more parameters, and you don't want to introduce more parameters early on because your model is not great enough at that point. So you don't want to introduce more parameters early on. That's the idea.
Yeah, and it's also good. TLS relies on having the atoms kind of in the right place. So you want to make sure the model is reasonably correct before trying to do that. There was a question about running X-triage on serial data. I assume that you mean XFEL or serial crystallography data. Yes, you can run X-triage on that kind of data when it's been merged. I'm not sure you'd want to put a massive unmerged serial data set into X-triage. It's not really designed for that. But assuming you've merged the data, then yes, you can of course run X-triage on that, and it's very useful. There are a few questions about occupancy related to ligands, and maybe we should save those till later on.
Because I did put a link in there so that people can read about that exact topic.
Yes, great. Thanks, Nigel. So yeah, Nigel put a link into one of the newsletters. For those of you that haven't come across the newsletter, Nigel puts this together, edits this. We do this twice a year, and it's a collection of articles. So these aren't peer-reviewed; they're just self-published. So it's some from the Phoenix team, but other people contribute to that, and that's actually a great resource. Maybe you want to put the link just to the newsletter part of the website, Nigel, so people can check that out. There's a lot of very useful information in there. If the data are very anisotropic, and there's an example given here of 2.5 angstrom in one direction, but 4 in the other directions, and they've been elliptically truncated, is there anything special that needs to be done in refinement when the model is close to final?
Yeah, well, that's a tricky topic. So we generally don't recommend anisotropy truncation. It may help in initial stages of refinement. So if you try to get from somewhere in initial stage towards more final stage, doing an anisotropy truncation may help get there, but it's a good idea to get as much as you can with anisotropy truncated data, but then go back to original data and refine your model with the original data. So Phoenix Refinement doesn't have a efficient tool to deal with severe anisotropy, although it does anisotropy correction for regular cases. For severe anisotropy, we don't have a very efficient way to do this. I think nobody has at this point. And again, the strategy would be you probably advance as much as you can with anisotropy truncated data, and then towards the end you switch to the original data and run final refinements using the original data, and then report everything using the original data. That would be the most honest and efficient way to handle this, in my opinion.
Yeah, and I think that just another thing to point out is that you may remember yesterday, I think it was Randy was talking about an intensity-based target function for molecular replacement that does actually account for the sigmas, and that's related to anisotropy, can be related to anisotropy in the data. And that's something that we're working on implementing in refinement. So in the future, we would definitely recommend probably using that intensity-based function for refinement that accounts for the weaker data and the large uncertainty in the data, and using that with the full data set, and not using, as Pavel says, not using a cutoff for the data.
Yeah, in a sense, it's conceptually similar to rigid biorefinement. So when you want to do rigid biorefinement, you do cut the data, right? So you don't use all the resolution up to 1 angstrom. You cut the data at 4 angstrom or 6 angstrom to do rigid biorefinement, just to help refinement converge. So conceptually, it's very similar with anisotropy. So you just want your refinement converge, and that's the reason you cut your data in case of anisotropy in a very specific way to advance your refinement up to a certain point. But once you are there, you want to use the whole resolution range.
Okay, there's another question for very high resolution data, 0.9 angstrom. Can I use Phoenix, or do I need to use another package like ShellX?
Phoenix can do refinement any resolution. I have refined a structure at 0.4 angstrom resolution or 0.35 angstrom resolution. So any resolution is supported.
So just looking here. Okay, so I think that's it for questions right now. So maybe you want to just go through a few quick demos, Pavel, and then we'll move on to Nigel. And we'll come back to some of these occupancy questions, I imagine.
Sure. Yeah, let's do it. Am I still sharing, right?
Yes.
Wonderful. So literally, I'm going to run through quick demo just to show how things look like and what you might need to pay attention to running Refinement. I'm going to run set out Phoenix GUI, but having Phoenix in my command line, and depending on your system, you might do it differently. Okay, I'm going to set up tutorial data. So as you know from yesterday, you can Phoenix comes with preset tutorials, and you can run a lot of different tutorials. So I'm going to run one of the refinement tutorials. Define where I want to run them. And the one I'm going to run is in Refinement, the first one, the easiest one to run. And I say, okay. And before we run Refinement, I'm going to illustrate how we do, very quickly, how we do validation. That's very important because I mentioned, Refinement and validation comes hand to hand. You always do validation. You need to know what problems you address when you run Refinement. So you don't want to run Refinement blindly without realizing where you are. So it's always a good idea to run validation. And if you run refinements sequentially, one after another, each refinement run comes with validation reports at the end, so you don't need to run validation specifically. But if you, just start out doing refinement from a structure you got from elsewhere, it's a good idea to know where you are to begin with, right? So it's a good idea to run validation and see what you have. So I'm going to run validation, and that's under validation tool is a comprehensive validation. So I click on that, and will pop up a usual graphical interface, right? So which asks you for a model. You give it a model, which asks you for restraints if you have those. In this particular example, we don't have any. So we give it a reflection file. And that's pretty much all you need to set up for the validation. The rest is just for your information. What's being instructed as data, R3 flags, and so on. So we are good to go. And of course, if you have entered file with multiple data sets, you can always choose which data to use, which R flags to use, and things like this. You can define, if it's neutron or X-ray data set, and choose on particular geometry parameters for that. So that takes very quick to run. So that's why one of the reasons why it's always good to run, right? For a particular reason, for this particular example, I'll go through some things. One is I mentioned the polygon tool that tells you where you are with the refinement, right? Or where you stand with respect to all other structures in the protein data bank. So for this one, that's how polygon looks like. And I hope you now agree it looks horrible. There's a very high clash score compared to everybody else in PDB. It has very high R3 factor compared to everybody else in PDB. It has very high R work factor compared to everybody else in PDB. So the polygon is bad. That means something is not quite right with your structure. The general idea, once you run this, you go through each and every tab. There's a open include button, and that's the first thing you do. So I did look at polygon, but really the first thing you do, you open it in Qt, and that will bring map and model. So they can explore how those look like, right? I'll make them up bigger. And the idea is, when every time you run it, you just go through all the tabs and explore all of them. And each one allows you to actually correct, most of them at least, allows you to correct your structure. So you just keep clicking, you click on null probability, and it tells, wow, you have a lot of Ramachandran outliers, you have lots of Rotem outliers, you have a full clash score. So everything in red is bad, essentially, right? You go to protein. I'm just picking randomly, but if you do it normally, just go systematically through each one. Click on Ramachandran plot, and you have Ramachandran plot outliers here and here, and they're all listed in this table here. What you can do, you can click, and they're all clickable. You can click on each one, and that will center you in the Qt and the map, and hopefully you can fix them in the Qt, or at least you can look at them and see what you think. Sometimes it's hard to fix them, admittedly. Just so you know, there are different flavors of Ramachandran plot for different residues. There's a general, there's a special plot for glycines, cis-prolines, trans-prolines, pre-prolines, isoleucines, and so on. So don't forget to click that thing to get different Ramachandran plots when you look at it. You can go to clashes, and there will be clash list here. So you can, I think it's ordered from worst to less worst. So, that shows severe clash. And you just keep going and looking where you are with your initial structure. And depending what you're actually doing, you may just look at it, or you may actually take an action and fix it, right? So that's the idea. That's how you do this. So now let's go close that validation report and do actual refinement. So that's located under Refinement tab on the right. So if you click on that, you'll see phenix.refine. That stands for crystallographic refinement, reciprocal space refinement. You'll see also real space refinement. We do crystallographic refinement, so I click on phenix.refine, and that again pops up very generic window where you can load in your data and model. You can give it model data open. That treats all these files and populates information extracted from these files. Again, if your data file has multiple arrays of data, you can choose which one you want to use in refinement right here. Same with R3 flags. It reports resolution limits of the data, but if you have a very strong reason to truncate the data by certain resolution, we never recommend this, but if you have a reason to do so, you can actually type in the resolution limits. There's more here. if you have experimental data, experimental phase information, I should say, that is usually formulated as Hendrikson-Lutman coefficients. So this would be here. We don't have it in this particular example. But that's pretty much it here. There's another section for neutron data, and this is something I haven't talked about, and that's my opportunity to talk about it, actually. So Phoenix can also refine against neutron data, neutron diffraction data, not only X-ray diffraction data. Can do it against electron diffraction as well, by the way. And it can also do what we call joint refinement. It can refine against X-ray and neutron data simultaneously. So if you have that situation, that's quite a special situation. You can also provide and load in your neutron data, and then you can refine against both X-ray and neutron data. Now, once you load all your data, the next thing you do, you go to refinement settings, and here is where major steps of refinement are defined. So by default, Phoenix is going to do 3 macrocycles of coordinate refinement in reciprocal and real space. It's going to refine B factors, it's going to refine occupancies. Again, it's going to repeat the cycle 3 times. For the B factors, it's going to refine individual isotropic B factors. For occupancies, it's not going to refine anything that is fully occupied, but it's going to refine occupancies of partially occupied sites, which includes alternative conformations. For reciprocal space, coordinate refinement is going to refine all the coordinates, and for real space, it's going to fit side chain rotamers only. Now you have extra options here, which I will talk in a minute. I'll run refinement just to save time, and then I will talk more about these options. So to run refinement, we just click Run button, and it has 2 options here. You can edit more parameters, edit parameters and run, or you can just run it right now. We'll run it right now. That will pop up Qt. And what that means is Qt is going to show you in real time how you see changes during refinement. So it takes a little time to load all the data and calculate initial maps. And then, I like to make map bigger. You may set up in your permanent preferences in Qt. But that's your map. So, and the procedure will update this map in real time. Okay, I'm going to go back to configure page settings and talk a little bit more about what else you can and sometimes should do. So refinement has about 1,000 different options, and there's no way we can express them all and show you all in the GUI window. So here we show, parameters that we think are most important, but oftentimes you have some particular situations where you need to adjust more parameters. And usually you find this in documentation or in just by asking us, and we suggest, well, you need to, to do what you want to do, you need to change that particular parameter. And then the next question you ask, well, how do I find that parameter, right? Well, that's the way. So you go to all parameters, and there's a lot of parameters that you can change here. Now, that still doesn't ask you answer your question. Sometimes we say, well, you need to change that particular parameter, and that's just a list of a lot of links to set of parameters like this one. Yeah. So what you can do, you can go and search parameters. For example, if I tell you you need to enable Ramachandran plot restraints or something like this, you can say Rama, and you get a lot of hits related to Ramachandran plot restraints. You can enable Ramachandran plot restraints, and you can be more specific in your search, right? So you can search for particular parameters, or we can tell you you need to adjust this non-bonded weight parameter. You go there, and say, hey, non-bonded, and that gives you non-bonded weight cutoff and all the hints related to non-bonded weight parameter. So that's the idea. So yes.
Can you search for free R flags so you can show how to generate them if you don't have them?
Ignore free flags of reads, can exclude free. Yeah, I don't see it actually here. It's interesting. Search parameters. Generate new free flags here.
Thank you. We just had a question on the chat.
Yeah, great. So yeah, you try to put something plausible in search parameters, and eventually you get what you want, hopefully. So yeah, you tick generate new R free flags, and that will do the job. But by the way, related to this question, so you won't be able to start refinement in the first place if you do not have R free flags. So if you start out refinement without R free flags, refinement will complain and stop, asking you to generate new R free flags or provide a new file with R free flags. So it's a good example how you search the parameter, but you won't be able to progress that far if you don't have R free flags. That's the point. Okay, so yeah, so there are more parameters here. Like I mentioned, things like NCS and secondary structure and reference model restraints. These are all the options that are available to you, but this is something you need to make a decision on your own. So, for example, if you have NCS, you need to decide whether you want to use it. Right. So in this particular case, this is a dimer. So there are two copies, there are two chains, A and B, and they are NCS related. So this is 2.5 angstrom resolution. So we ran a refinement without NCS, but we could have done it with NCS. And the way to do it would be to check use NCS button here. And that will say, well, we want to use NCS. Now, and it's totally critical, how the program knows what exactly is NCS related. Just think about it. So you have two chains, but what if they're different? What if there are mutations? What if this, they're not exactly sequentially identical? Are they still NCS related? Or what if they're sequentially identical, but just, coordinates are different? And if you superimpose them, they're not exactly the same. So the program has an algorithm to detect what is going to be an NCS related copies, but it may fail, and quite often it fails. So you always need to double check what the program thinks of NCS related copies. And this is how you do it. you check use NCS and you go to select atoms. And that should pop up the selection editor. And the first thing you see is find NCS. So when you run refinement, it will find NCS automatically, but this particular venue allows you to select NCS manually and verify it. And this is what I always recommend you to do. So you say find NCS, it has a parameters to find NCS, to exclude hydrogens or water from NCS, which makes sense, right? It has some thresholds for thickness and density and for differences between particular coordinates. You say run, takes no time pretty much. That gives you a selection. Now it gives you a selection, right? So it tells there's a chain A and chain B and this particular residues that are selected. Well, looking at the string, it's hard to make sense what that means. So we want to look at this graphically. We click on the model, and that pops up Phoenix-Belen model viewer, and that allows you to actually see these selections. So we click on the first one, and it selects everything, but for some reason it excludes this one residue, there's another residue, and there's another residue. You click on the related copy, and it also excludes those residues. So just physically, it will be more meaningful to actually include these residues, and there's no point to think those residues are going to be very different in this context. And if they are different, then NCS machinery uses torsional NCS restraints that potentially allow for differences. So it may be a good idea to actually edit these restraints and say, well, I want to use chain A and chain B as is, and let the NCS machinery to exclude these residues if needed. But these are all the options you have, so you can play with this and define what you want to do. So you can just close, or you can save and close, which means you'll be actually using these NCS restraints in your next refinement run. Now we have our refinement run finished. So you can go to refinement outcome page, and there's a lot of information to look at, obviously. So, and I will send you back to remembering what we've seen for the initial structure before refinement. First thing we looked at the polygon. Remember, it was an awful polygon. Now it's a much better polygon. So we get R factors kind of below average. It's great. Even class score is below average, which is also good. So polygon tells us we are good. But the polygon picture tells you, kind of summary of basic information, global picture. So you are good on a global scale, but we still need to do and go and look locally. So polygon tells we are all good globally, which is great, but we do still need to look locally. And that means we go through all the steps. We always do this after refinement. We got our own probability, and it still shows us some amount of Ramachan outliers. It's much less than in the beginning. We still have some Rodham outliers and so on. So that means we still need to go through the structure and investigate it and fix the problems. So we want to go to protein and look at Ramachan plots. So we have an outlier here. We want to go, as again, it's listed here, clickable, click on it. And if you can, you may want to fix it manually. if you cannot fix it manually, don't get stuck with it. Do something else and come back to it later. Maybe a map improves later on. Because remember, we ran the refinement without doing water peaking, right? We haven't updated waters. You know what that means? We don't have water in our structure. Well, some people do it in Qt, which I think is a waste of time, because you can do it automatically by letting refinement fill all these green densities, which makes sense geometrically, with waters, and then later on you can go and check all these waters and either keep them or delete them. So we don't have time right now, but the next refinement run would be to take the structure and go and run it with water peaking. So that refinement places all the waters here. And that may improve the density map. It's going to improve the density map so that you can do more fitting of the protein to improve it. And that's the idea. A lot of other things that you might think of, but I think we're running out of time, so I'll let Paul to decide whether we look more or we take questions.
Okay, great. Thanks, Pavel. So here's my suggestion. I think, why don't we take a quick break and come back at 10 o'clock. Before we do that, let's thank Pavel for a great set of presentation and demos there. So let's come back at 10. I think we'll start off with Nigel then, and then get to Chris, and then we can return to the questions. We'll have a long question and answer session after those two presentations.